Okay, we're going to learn about forces in the y-axis. There's a couple of them that we're going to be studying. You're going to be able to draw free body diagram, label the forces, and then solve for missing variables. All right. Follow the directions, draw a diagram. So here's Tigger, Winnie the Pooh. How much does he weigh? So we're trying to look for FG. Weight always points down. And technically, if I really wanted to be precise, right, he weighs down, and then he's got this spring that pushes up, up on him. And he's balanced. So like the spring pushes up from the bottom. And that force of the spring pushes up, and the force of gravity pushes down. But it looks kind of confusing that way. That's supposed to be a spring. Yeah, that's crazy. I don't have time to read it, but that's a spring. Spring. So you have force of gravity down, force of spring going up, and it's supposed to be perfectly balanced. But to make it clearer, I'm just going to put the force of spring, pushing it up like that. But, technically, he's balancing on a spring scale. All right, now he stays perfectly still. So that means my force net, MA, still, perfectly still, A is 0. Anything times 0 is 0. So my force net is 0. I'm going to write it in black, in green, or whatever this is. So force net equals 0. Now I write my two forces, going up and going down, and they're both balanced out. So I say force of the spring is going up, positive, usually, that's for sure, plus a negative force of gravity going down equals 0. And then if you want to know what one equals, you just say, add force of gravity both sides. All right. Now what? Force of the spring equals force of gravity. Yeah, okay, they're balanced. Now what? Well, oh my goodness. So what else do we know about the force of springs? Well, they tell you the spring constant. They tell you K. K is 200 newtons per meter. That's inherent quality of the spring. What else do I know? How's the spring? Oh, it's compressed to 12 centimeters. And I converted that to meters. All right, so 12 centimeters divided by 100 centimeters and 1 meter, and you're going to get 0.12 meters. Now, F spring is not given. Oh, what's force of gravity? So what other things do we know? We also know gravity is always 9.8 meters per second squared. And what else? We're trying to find mass. Mass we don't know. So I have 4 things I kind of know. And I'm trying to find the weight. I'm trying to find FG. Well, I don't even need the mass. So I'm just trying to find this. I'm trying to find that. I'm trying to find weight. Weight is my FG. So my weight is also equal to my spring. So I could write this force. So if I find my force of my spring, I could find my force of gravity. Oh, I know. I could use my handy dandy reference table and identify the force of a spring. Where is that? Oh, right there. Way down here. How do I know? I look way up here. Force on a spring. That is my spring constant times x. So now I could replace this side with kx. So now my force of gravity, because these two are equal, is going to be equal to my spring constant, 200 Newton meters, times my compression of 0.12 meters. It's my FG. All right, we do the math. Meters cancel out. You're going to get a Newton. All right, now let's do the next one. A mass of 10 grams is stretches a spring of 4 centimeters. What's the spring constant? Oh man, another one of these? Yeah. So here's your mass, or I'll draw the real diagram. Looks like this. There's a spring, right? And you got a mass going down. It's 10 kilograms. Right? So you have a force of gravity going down, force of spring going up, and it's stretched. So I'm just going to draw force of the spring going up, force of gravity going down. Now, are they equal? Well, is it moving? It doesn't really say. It's just stretched and it's hanging there. So force net equals 0. So that means the force of the spring equals the force of gravity, vice versa. These are balanced. And you can watch me do all that little fancy work, but really all it means is these things are equal to each other. You know, why? I add them up, set it equal to 0, then I subtract 1 over, and it just says the force of spring equals force of gravity. I don't have to do any more work. But now I'd say, what's the spring constant? Holy mackerel. Well, now what do I do? Well, there's 2 equations I know. Force of gravity equals mg, and force of the spring equals kx. How do I know that? Well, you've hopefully been studying it. This is very annoying. Don't like that. But this is what? Force of gravity equals mg. Why do they have to write it in this form? I'm not really sure. But that's mass times the acceleration, and in our case, it's gravity, 9.8 meters per second squared. Ah, there you go. So we have these 2 equations. So, since these 2 are equal to that 2, I just put right underneath it, I could say, Kx is my spring, and that is equal to my mg over here. What's the spring constant? Well, you're trying to solve for k. You don't know what k is. So you're going to do mass is 10 grams. The x, the distance, is 0.04 meters. I took 4 centimeters divided by 100. That gave me that. K, I'm looking for. And G, we know, negative 9.8 meters per second squared. Now, why? Like, this is a little crazy, but I just kind of know. I don't have to put the negative in because I'm just looking at what's going on in here. I'm not actually asking for directions. I'm just looking for a spring constant K. So let's put that down. Have K is equal to 0.04 equal to mass, 10 kilograms times 9.8 divided by 4, 0.04. That cancels out. K is equal to 10 kilograms, 9.8 meters per second squared, divided by 0.04 meters. So that's kind of weird. You're going to leave the Newton at the top and meters on the bottom. Put that in your calculator. I shouldn't do that for you. Let you guys work it out. And your final unit, kilograms meters per second squared, is going to be Newton, that's the top unit, divided by a meter. There's your K. All right, let's do the next one. A spring with a constant, oh, there's your K right now, 20 Newton meters. Oh, it's the same unit as over there. Stretches, got to convert that to meters, 0.038 meters, divide by 100. When it's hung, calculate the mass. Oh, it's the same question. And gravity we know is 9.8 meters per second squared. Have the same setup. Force of gravity, force of spring. Why? They're still, so they're not moving. So the force of the spring will equal the force of gravity. Substitute these equations in. Force of spring is Kx. Force of gravity is mg. I'm trying to solve for m. So I put my numbers in now. 20 Newton meters times 0.038 meters equals my mass, I don't know, times 9.8 meters per second squared. Now, if you put negative in here, you'll be okay. But technically, we don't really care about directions right at this moment because I'm showing that with forces. So the meters are canceling out. You just left with the Newton here. And then you're left with a kilogram. So divide by 9.8 sides, 9.8. So let's do your math. 20 times 0.038 divide by 0.98 meters per second squared. And you get this for your mass. You get mass is equal to 0.0, I might round, 8. And the unit is Newton divided by a meter per second squared, which is also Newton is a kilogram meter per second squared divided by this number, meter per second squared. And then those cancel out. I'm just off with a kilogram. So the final answer, 0.08 kilograms. Bell's going to ring momentarily for me. Woo! What's going on here? Suspended by a rope. What's the force of tension? So this time, force T. Sometimes I write a capital T here. And force of gravity. Suspended means it's not moving. Your force net equals 0. Force of tension plus a negative force of gravity will equal 0. Add force of gravity both sides, force of gravity both sides. The force tension will be equal to force of gravity. What do we know? If here's your mass, is 15 kilograms. Gravity is always 9.8 meters per second squared. No, I don't worry about the negative because I'm not worried about directions right now. And so if I'm trying to find the force of tension, I'm trying to find Ft, I don't have to do any work, really. What's my force of gravity? Well, I have these equations. Force of tension, no equation. You guys got to do it. Tension. But the force of gravity has an equation, mg. So, walk over here, put mg in, go 15 kilograms times 9.8, which is basically 10, which makes the force of tension on the rope approximately equal to, 150 meters per newtons. About, 15 times 10. It's about. You get the answer. Your answer. Now the bucket is accelerating. Woohoo! Now what do? You have the force of the bucket. You have force of gravity being lifted with an applied force, 525 newtons. Oh, I'm going to put force A, newtons. What's going on? So now I have force net is equal to ma. There's an acceleration here. Still going to apply it. Force applied plus a negative force of gravity is going to cause my mass to accelerate. Don't get all freaked out. This is not that hard. You put in, what's your force of gravity? Force of gravity is mass times gravity, 45 kilograms times 9.8 meters per second squared. Force of gravity. Force of gravity. That's, like a basically 450. You get your actual number, right? I don't have enough time to do this whole thing. So force applied is 525 newtons plus approximately 450 newtons is equal to, this is approximate, so you do the math, and then my mass, 45 kilograms. Oh, we did that in class. Hey, get that together. Oh yeah, and that's supposed to be negative. And then divide through by acceleration. Woo! Now, a kid's being airlifted up with a rope in emergency evacuation. Apply the force is 800 newtons. Now you got this thing. He's going way up, 800 newtons. He's got a weight. The force of gravity is mass times gravity, which is 35 kilograms times approximately, 10 meters per second squared. I'm just trying to go fast. Is 350 newtons. So when you do force net, you have an acceleration. You're going to do your two forces, force applied or the tension on the rope or whatever that is, plus a negative force of gravity, and then that mass is going to accelerate. You have approximately 800 newtons plus a negative 350 newtons. Bring them together, then you have your 35 kilogram kid times your A, divide by 35, divide by 35. Blah, there's your A, blah. All right, kid in an elevator. When the elevator is rest, what is the weight of the person? Force of gravity is mg, just hanging out there. Mass, 80 times 10 is approximately, you get this, 800. Mass is 80 kilograms times gravity, 9.8, approximately. Now, if the floor accelerates upwards, does it feel more or less weight? You feel heavier because you're zooming up and you feel that pressure down. So you feel like you have more weight, more. You feel more. And then what happens when it drops? I mean, you feel like you're like, whoa, you're floating. You like way less. All right. Now, what happens when the scale reads 500? So if you originally weigh 800 newtons, it's going down. So if the scale weighs, if a scale weighs, you're supposed to have 800 on your scale, and it weighs less, you're going down, you feel less. Now, what happens if the scale weighs nothing on it? And you're falling.